vacuum techniques. I am to introduce you to the techniques in ultra-high vacuum systems. First, this video will show the uses of vacuum systems and some general information about how low pressures are achieved. We begin by addressing the questions: what are high vacuum and ultra-high vacuum, why are they useful, and how do we build vacuum systems? High and ultra-high vacuum are just terms for two different pressure regimes. High vacuum systems have a pressure approximately within the range of 10 to the minus 6 and 10 to the minus 9 torr. Ultra-high vacuum, or UHV, is the term given to the pressure range less than 10 to the minus 9. Why do we use vacuum systems? There are a number of applications that require the use of high and ultra-high vacuum systems. This is because of the incredibly low amount of the interaction between experimental samples and low-pressure gases. At atmospheric pressure, gases interact with experimental samples, coating them with layers of contamination, changing the surface chemistry. To counteract this, air can be pumped out of a closed system. In a chamber at high vacuum, there are a few gaseous contaminants to interfere with experimental samples, but samples can still be completely coated with contaminants in just a few seconds. The lower the pressure, the more slowly a sample will be contaminated. At UHV, it can take several hours for surface contamination to take place, making a detailed study of sensitive surfaces possible. This allows for atomic resolution encoding techniques such as atomic force microscopy and scanning tunneling microscopy. This also allows for excellent purity in growth mechanisms such as chemical vapor deposition. These and many other techniques are used under high and ultra-high vacuum, making it very important to note just what is required to build and maintain a vacuum system. So, what is involved in building a vacuum system? The most fundamental component of a vacuum system is a chamber, which is typically made of stainless steel or another material that is strong and does not release any gas into the chamber when it is at low pressures. In this chamber, devices of all kinds can be mounted on flanges and filled through vacuum tight by the use of copper gasket. On each flange is a metal ridge called the knife edge. When a copper gasket is placed between two flanges and the flanges are tightened together using bolts, the knife edge digs into the copper, creating an excellent seal. This type of flange is called conflap. Other flanges exist that create the seal by using different types of gaskets and different mechanisms to tighten the flanges together, but the general principle is usually the same. The chamber and the flanges can be sealed as airtight, but they are pointless without a way to evacuate the gas from inside the chamber. To do this, there is vacuum pumps must be used. Traditional mechanical pumps have a high throughput, but they cannot attain UHV on their own. Therefore, these pumps are used to pump chambers down from atmospheric pressure with the help of other pumps. A number of pumps can be used to get the UHV regime, including turbomolecular pumps, diffusion pumps, cryopumps, and ion pumps. Each of these has different principles of operation and advantages and disadvantages. Ion pump was considered to be the real workhorse of a UHV system because it introduces no oil contamination and has no moving parts. They are also capable of attaining terminal pressures lower than 10 to the minus 11.
Hi, my name is Choo. Let me explain to you how an ion pump works. Basically, this is what an ion pump looks like in the outside, which is essentially a stainless steel chamber. However, on the inside, you will find a lot of additional components that are certainly you cannot see. We start with the feed-through and an anode assembly made out of stainless steel anode tubes. Those are isolated from the rest of the system. The green point is the cathode, and it is a ground potential along the rest of the system. In external, two of those are magnets and pull pieces, sometimes called flux plates, that are on the outside of the vacuum chamber. Looking at the side view, we start off with the grounded vacuum chamber. So this would be your stainless steel wall, isolating atmosphere from the vacuum inside. On the outside of the chamber, we are going to add very strong ferrite magnets. Now those magnets are going to create a very high magnetic field and concentrate the field at targeted area only, which is between the magnets. We put a magnetic steel pull piece or flux plates around that to capture again on the inside. That is our grounded cathode plates. And internal to that, we are actually going to start drawing our electrically isolated anode rings. If we go ahead and take a close look at this, you will see that in this configuration, there is strong magnetic field between those two magnets at about 0.12 Tesla goes through the anodes, cathodes, and vacuum chamber walls. Zooming up on that, we are going to actually rough this pump down to 10 to the minus of 4 torr or lower if we can, and go ahead and turn it on 7,000 volts is what we typically use, but the ion pump will operate in between 3 and 7,000. Free electrons are going to get pulled towards that anode assembly. They are going to be caught in the magnetic field and rotate around it. This is actually called magnetron motion, and the electrons get trapped until they actually hit something like a gas molecule. And because there are so many electrons moving around in the electron cloud, they are bound to get hit and has molecule eventually. In our example, let's go ahead and use oxygen. Here's our oxygen molecule in green, those who are actually in motion and they are going to collide. When they collide, they are going to create a positively charged ion, and we are going to go ahead and draw that ion here in red. And remember, that is in a positively charged anode tube, kind of like putting two magnets together. Two north poles don't want to go together, and what is actually going to happen is that positively charged ion is going to move towards the grounded cathode plate at a very high velocity. And when it hits the plate, it's going to sputter, and there's going to be two things that happen. One is a chemical reaction. We use titanium as our material, that is oxygen, going to chemically combine with the titanium. And at the same time, there is going to be a physical reaction, and that impact is going to spray or sputter titanium molecules all over. And over time, enough molecules are going to sputter onto the titanium that you will actually have a build-up of those titanium compounds and titanium directly all over the walls of those anode tubes. And over the years, the cathode will eventually have craters formed from all the impacting ions.
Hi, my name is Bagner.
Greetings there. So today I will explain about this sputter cleaning. So in this case, the Heracer sputter targets are used for the sputtering cleaning for the photovoltaic and electronic systems. So basically the transportation of the substrate into the chambers, which is the sputter chambers. So during the whole process of this sputtering process, the air will be evacuated continuously from the chamber by vacuum turbo pumps. So you can see the air will suck out from the chambers, and at the same time a certain amount of argon gas is fed in continuously. The strong magnet bars are placed inside the tube, and so that the targets are flushed with cooling water and begin to rotate. At the same time, there is permanent magnets create a magnetic field through the target, and with the high voltage is applied to the target, the argon gas becomes ionized, and thus a plasma forms along the magnetic field. And at the same time, these argon atoms are hit by free electrons and will create a transfer from the target materials to goes down to the substrate. So this phenomena, we call it as a sputtering cleaning process, the ejection from the target materials. So you can see at the different angles the target atoms goes down on the surface of the thin layers of the substrates, and then the substrate moves steadily from sputtering chambers results to the uniformly coated with applied target materials as sputtering cleaning surface. So in this process, we can say that the cleaning of the solid surface in a vacuum by using a physical sputtering of the surface by using the Hiraeus sputtering targets. Thank you. In this measurement of vacuum, it works in a pressure range between 10 to the minus -2 until 10 to the minus -9 torrs. So this system consists of the anode, cathode, magnetic pole, high voltage, and emitter. In this working principle, the ions always present in the gas. So when the electric potential of 2000 volts is applied between the anode and the cathode, then the gas discharge equals. Since the ions are always present in the gas, then the ions accelerate towards the cathode. Upon interacting with the cathode, electrons are emitted and accelerating towards the hollow anode. The presence of magnets will make sure the electrons move actively, which increase the charge to hit the gas molecules to ionize it. And then this emitter is used to measure the ionic current, which is converted into pressure units. And finally, the pressure units is either in units of pascals or torr. So this is the basic principle.